Hello and welcome to PyCon 2021. My name is Rebecca Bilbro, and together with my co-presenters Daniel Sollis and Patrick Deziel, we are going to be presenting a talk on PyTesting, the limits of machine learning, which is informed by our experience working together as a team, building machine learning products for industry and writing tests against those products. To give you a sense of how the talk is going to unfold, I'm going to start by giving a short introduction to motivate this question of why we test machine learning. And then Daniel's going to talk about building a testing API. Patrick will talk about dealing with non-determinism, and I'll talk a little bit about how to do experimentation while still doing testing. And then we'll leave you with a few tips that you can take with you after the talk. So, this question, why test ML, comes to me a lot. And to be fair, it's a question that I used to ask myself at the beginning of my career as a data scientist. And I think it's an important question for us to really tackle head on at the beginning of this talk. The first family of questions that I get kind of in this vein are, do we really need to test our machine learning code? Usually these questions kind of follow these similar patterns. People say testing is for software. It's not for science. It's not for data scientists. We're scientists. We do science. We don't do software. I heard people say that what their teams do is hypothesis-driven development. They're testing out hypotheses. They're not testing their code, which is a different kind of a best practice altogether. And I've also heard people complain that, it hinders the experimentation process if you feel like you have to write tests against all of your experimental research code. I think these are important kind of things to listen to. I've also heard kind of a family of concerns that really fall into this category of, is it even possible to test machine learning code? I've heard engineers say that, these algorithms are non-deterministic, and so there's no way to test them. I've heard people raise concerns about the sheer number of parameters that you would have to test and the combinations of parameters that you would have to test in order to kind of cover machine learning algorithms. And then other teams complain that the tools that they're using, for example, Jupyter Notebooks, don't support robust testing. You won't be able to run a test runner against your Jupyter Notebook. At least not yet. And so these are kind of the concerns that I'm hearing from the community. And really what I'd like to say is I think these are all valid. I think that when we build machine learning projects, the dream is that the models that you're building are going to go and be useful for someone, right? It's not just about winning a competition or kind of having a flashy presentation. You want to build things that make the world better. You want your models to do good. And if you are going to be building models that have the potential of going into a user-facing product, even a few iterations down the line, you need to think about testing from the beginning, right? We need to make sure that we're protecting the consumers, the eventual consumers of our models. And so that's why we need to test ML. And so if there's any potential that this could become, part of a product or be in the hands of a user, we do need to write tests. So next, I'm going to pass it off to Daniel, who's going to talk a little bit about what the building blocks of something like that might look like.
Thanks, Rebecca. My name's Daniel Sollis. Just as a bit of an introduction, I've been working at Unisys for coming up on 2 years now as a systems engineer. My job really focuses on AI ops and building proof of concepts for machine learning projects. And I'd like to go over a few things that I found really helpful in getting that job done, particularly in regards to testing. So one of the most important aspects of a good test suite is the structure surrounding the tests that ensure the tests are easy to write, maintainable, and enforced. I'll go over some features in the sklearn library, which make testing machine learning code a whole lot more manageable, as well as some other ways to standardize your testing process. The sklearn estimator and transformer classes collectively contain the fit, predict, and transform methods. Overriding these three methods are really helpful. They allow you to generalize sklearn's various models and transformations for consistent use across preprocessing as well as modeling. This really reduces the number of tests required, as well as simplifying the tests that do need to be written. So here we see the basic idea of creating a wrapper class. Basically, you just inherit from the estimator and transformer classes, and then overload the predict, fit, and transform methods. This creates a catch-all for sklearn's various classes, basically allowing you to wrap both transformers and estimators and get some additional metadata that sklearn doesn't surface. For instance, in the fit method, you could actually just get the fit time with very little work, which can be helpful for testing later. Similar with the predict and transform methods, it really allows you to do anything. The next feature I'd like to highlight are pipelines and feature unions. These let you organize the pre-processing and modeling stages so that you can really just iterate very quickly through experiments. Not only does this reduce time spent coding, but it also makes writing tests a lot easier. Pipelines are great for simple uses, while feature unions are really designed for more complicated purposes, and they specialize in parallelizing steps. By using a wrapper class, like we mentioned previously, using these features becomes a lot more streamlined. So here's an example of a pipeline. As you can see, this pipeline basically just extracts some data from a series of essays, translates those into a count matrix, and then takes that count matrix and turns it into a TF-IDF representation. And then finally, we train a multinomial naive Bayes classifier with that. As you can see here, like a pipeline really reduces the amount of code required to perform pre-processing and training of a model. And obviously, this is going to apply to your tests as well. So here's an example of a feature union, very similar to the pipeline from earlier. You can see through the code that it's basically really just a nested pipeline, which is why it's really good for parallelizing different steps. So in addition to using the different features from sklearn that I mentioned previously, another big part of maintaining a healthy testing suite is making sure your repository maintains high coding standards. So what we decided to use to help with this were the black formatter and pre-commit. Pre-commit just to ensure that black is run every time anyone does a push. Yeah, it really helps ensure that the repo maintains like high coding standards and is clean across different commits from different people. Now, while black is really great at maintaining a clean repo, it does have its downsides. It's pretty strict and might not be for everyone. There are some alternatives to black, such as YAPF, which is maintained by Google, as well as AutoPep8. These would be good for people looking for something a little bit less uncompromising than black. One final thing I'd like to highlight is really the importance of CI/CD. For this, we ended up using Jenkins. You can see on the right our CI/CD flow. For each push, pre-commit would launch black to format the code and ensure code cleanliness. And then Jenkins would create a build and run our tests. This is really an incredibly important part of the process. Jenkins is an extremely useful way to ensure that testing is enforced. We actually managed to find a couple of issues with some libraries we were using, the versions we were using that we wouldn't have found otherwise. Plus, automating builds really helps ensure that code works in different environments on different machines. Now I'll pass it off to Patrick so he can go over dealing with non-determinism.
Thanks, Daniel. Hey, everybody. My name is Patrick Deziel. This is my first PyCon, so I'm pretty excited. I've been working at Unisys for a number of years. Most recently, we've been working on proof of concepts in Python for machine learning applications. And so, like Rebecca mentioned earlier, testing machine learning code can seem like it's pretty intimidating, but it's important not to get discouraged by it. So I'm going to show you some techniques you can use to deal with some of the weird stuff like non-determinism when you're looking at testing machine learning code. So let's say we have the example where we have a bunch of images of different things, and we want to classify them as either muffins or chihuahuas or dogs. So we can write a good scikit-learn pipeline for this, but the real question is, how do we handle non-determinism when we're testing? How do we handle the multiple parameters that our scikit-learn APIs require? And how do we handle the small variations that could occur when we're running our pipeline over and over again? So the first type of non-determinism that you might encounter is if you have a data set that you're splitting into train and test, but you're doing it randomly each time you execute your for your pipeline. So if you're feeding in different data to your pipeline, obviously you're probably going to get different results out of that, which is not conducive to testing. The second type of non-determinism is if you have the same data that you're feeding into the pipeline, but your underlying machine learning algorithms have some type of random process to them, like for example, stochastic gradient descent, so that each time you run your pipeline, you're getting different results, which is difficult to test because you don't really know what to expect. So you don't know what to put in your test. So one thing that you can do with this is you can fix the random seed, and that will ensure that in all your non-deterministic functions, you're going to execute code the same way, because you're fixing all the points where you're making a random decision. So one way you can do this, if you're using scikit-learn, it has a random state parameter which they provide, and for each of their non-deterministic functions. And so all you have to do is look to see if it's supported in the giant list of parameters. And if it is, that's good. Then you can set the random state that way very easily. If you set it to some constant, then each time you run your pipeline or your tests, it's going to produce the same results. So let's say we take our muffins and dogs example from before, and we can write a very simple function which takes in a data set of all those images, and we extract features from them, we create our train and test splits, and then we run an MLP classifier on it, and then we return our predictions based on the test set. So we can add the random state to both our train test split and our MLP classifier. And what that does is fixes both those functions so that we're producing the same results each time, and we would expect this function to behave the same way on multiple executions. So then that allows us to slap a test onto this function. And this is pretty simple if we're using PyTest, because we just have to define what our expected results are. And we have a situation where a dog is 0 and muffin is 1. So we just set our expected list, and then compare to that once we've executed our muffins and dogs function, which we wrote earlier. And this works pretty well, but this in reality is going to be a very simple case. You're much more likely to have a more complicated situation where you're passing in multiple parameters to maybe your NLP classifier or other things. So the real question is, how do we handle these multiple parameters without turning our test code into just complete unreadable nonsense? So one thing we can do here is utilize the parameterize marker within PyTest. And this is one of those most powerful things that I've discovered with PyTest, because what it allows you to do is identify sets of parameters which are passing into the same test function. So you don't have to write a test function for every single set of things you want to pass into your muffins or dogs function. We just have to write one test function which is taking in whatever parameters we're defining, and then define each set of parameter sets that we're passing in. So for example, I might use this with different data sets, or I might want to try out a different classifier like a random forest classifier, or one cool thing that we can do here is we can redefine our muffins and dogs function to take in like a generic scikit-learn estimator, and also generic parameters. And since we define our parameters as more of like a dictionary, it's very easy for us to define it up in the parameterized code. And we can use this to set whatever parameters we need for the estimator. We can also use it to set that random state, which we talked about earlier. And this gives us a very concise way of writing tests and makes them very easy to maintain, modify, etc. So one thing that you also might encounter with machine learning is, since there's a lot of floating point arithmetic under the hood, things can get a little strange. Things might not work exactly as you would expect based on your math class because of the ways floating points are handled under the covers, and depending on what precision you have for floating point in your Python. So in order to correctly test machine learning code, we're going to need a better way of comparing floating point results. And what that boils down to is that we need a way of handling results that are close enough to what we'd expect them to be. Another way we might use this, we might need this, is that if we're, let's say we're trying to time how fast our algorithm is going to train. Since if we're basing it off of wall clock time, it's going to be a bit different every time, but we need it to be close enough, maybe within like 0.01 seconds or something. So another thing that PyTest provides is the Prox function. And what this allows you to do is write a bit of shorthand for making these weird like approximate comparisons. Before we'd have to write maybe like an absolute value notation for this and then compare whether or not that result is less than 0.01 or whatever our expected relative tolerance is. So the problem with that is that when you're looking at this code, it's hard to understand what it's doing, and it's also hard to understand how to change it. So if we use the approx, it's a bit more readable and allows us to do what we wanted to do, which is just compare two values within some relative range that we pass in. So hopefully you'll find these techniques useful when you're dealing with testing machine learning code, and makes you a bit more confident in actually being able to test all the aspects of your ML code without having to resort to not testing it, which would be probably not advised if you're trying to put something into production. So now I'll pass it over to Rebecca to talk about diagnostics for machine learning.
Thanks, Patrick. At the beginning of this talk, I said that if you are going to be building models that have the potential to go into a consumer-facing product, you need to write tests. But I do worry that, there is a possibility that you might take away from this, that I think that there is sort of a trade-off, that you can either do good engineering, that comes with testing and, code formatting and all of these things, or you can do good experimentation and be a good scientist. What I would like to suggest is that that might actually be a false dichotomy, and that there are tools out there, open source tools, that can help you kind of do these two things simultaneously. One of the tools that I'm particularly excited to talk about is the Yellowbrick project. Yellowbrick is a pure Python open source project that sort of takes the best of scikit-learn together with matplotlib and allows you to visualize your machine learning models and understand what's going on under the hood. It helps with diagnostics, it helps with algorithm selection and hyperparameter tuning. This is a package that I co-wrote with a colleague, Benjamin Bengfort, about 5 years ago now, and actually announced at PyCon many years ago. And since then, we've amassed many contributors from all over the world. And really, the main thing that we've tried to do in the Yellowbrick API is abstract out some of the very common machine learning workflow patterns. One of those is trying to understand what's in your data, right? So taking your data set, performing transformations, and seeing if the transformation was successful at removing outliers or removing noise, at making the clusters cohere more, at reducing multicollinearity. So that's one of the patterns, workflow patterns that we support with the Yellowbrick API. The second one is allowing you to compare different pipelines, right? To kind of use some combination of transformers and couple that with an estimator, and then evaluate how well that model has performed. And that could mean comparing completely different algorithms together, or comparing one algorithm with variations on different hyperparameters. And so what does that look like in practice? Here's an example that takes Patrick's dog and muffin classifier and allows you to compare two different algorithms, a random forest classifier with a stochastic gradient descent classifier, and see how the two different algorithms performed on the same data set. And I hope that you see right away that there's a lot of nuance that goes into this visualization that you can't get if you're just looking at a high-level F1 score, right? So already we can see that there's nuance related to the precision and recall across our different classes between these two models. These are probably things that you want to be aware of in terms of experimentation. So how do we wrap in that experimentation into a testable flow? So let's look again at Patrick's function that differentiates muffins and dogs and does model training under the hood. So what we're going to do here is, in addition to importing our scikit-learn classifiers, we're going to import a Yellowbrick visualizer called the classification report. And so in our function, the first step is we're going to create a figure, and inside that figure, we're going to be able to plot this data, and then we'll store that image to disk. And so that will run in parallel with our training code. So we split our data into train and test. We instantiate a visualizer in the same way that you're used to instantiating classifiers. You pass in our model, so whatever the model is going to be that we use in the parameter here. The classes, we can pass in a color map optionally. We can pass in the axes for the figure that we've just created. We can turn support on, which will tell us how many data points went into each training. And we can select show equals false, which will allow us to suppress the show function of Yellowbrick and allow us instead to store the image to disk. We'll call fit on the visualizer, passing in the train data, and then we'll score it using the test data and output the results of that visualization to disk in our path. And then we will also return the predictions from y-test, which is what the original function did. And so we haven't changed anything in the original function, except that now we also will have this image to compare after the fact, which will support experimentation. So just a few final tips before we leave you. The first is to leverage a machine learning API. Scikit-learn is one option. It's the one that we've looked at today in this talk, but there are other options. So using some kind of open source machine learning framework will give you the building blocks for doing systematic testing of that machine learning code. Pipelines serve in a similar way. They allow you to chain the steps together and allow you to detect things like the possibility that there's leakage happening and prevent those from bleeding into your code. You can also drill into fuzziness using the excellent tools that come in, for example, the PyTest library, which allows you to run tests against multiple different parameter options and also allows you to tolerate fuzziness and approximate results, which is really useful. We embrace consistency, right? So all of the things that aren't about machine learning, right? Code formatting, all those preferences, we come up with a agreed upon system in the beginning, whether that's, PyFlakes, whether that's Black, whatever it is you like to use. And we embrace that from the start so that we can really focus as a team on looking and assessing the state of the machine learning code. We use CI/CD to help us identify dependency changes and test regressions so that we don't have to be manually monitoring those. And finally, we use tools like Yellowbrick to help us marry the best of both worlds with engineering and experimentation. And that is all we have for you today. Thank you very much for coming to our talk, and we hope that you enjoy the rest of PyCon 2021.